Hello and welcome to this lesson on two alternative tactics that you'll want to consider in problem solving questions on the GMAT Quantitative section, modeling and backsolving. So let's begin by talking about quantitative modeling, or as it is colloquially known in many cases, plugging in easy values. So firstly, this is an alternative tactic for some of the more complex arithmetic, algebra, and geometry problems that you'll find in the problem-solving format on the quantitative section. You want to use it primarily for problem solving, and you'll want to generally stay away from plugging in easy values when it comes to data sufficiency. There are just different tactics that you want to apply for the different formats on the quantitative section. And there is an approach for plugging in for data sufficiencies, but that is a bit different and involves different values. So you want to stay away from this tactic for data sufficiency because it often can be inefficient. So just apply these techniques primarily to the problem solving. Now, you'll want to do so as soon as whatever algebra you encounter, or just the math generally, becomes no longer apparent or simple. So what that means is, as we talked about in one of our earlier lessons, apparent means that you can set up the math, and simple means that you can solve it. So if you can do neither of those things at any time, you may want to consider if plugging in easy values might be a way to work the problem kind of from the back door. So here are some clues that indicate possible modeling opportunities. First are identifiable variables in the choices and or the problem. Now, those can either be assigned as actual letters, as you'd be familiar with when it comes to algebra, X's, Y's, A's, B's, or they could just be unassigned, unknown values in a word problem. So if they're talking about someone's age, you may not know what that age is, and that could potentially be something that you could model. So often that word problem unknown is a total, so something like the total number of marbles in, say, a jar is being allocated in some different number of ways. You could potentially avoid the algebraic approach by just defining the total and then determining the impacts one modeled approach for a specific scenario that exceeds to all of the conditions of the problem. So some key terms that you'll want to recognize are going to be the phrase in terms of. So if you've got, say, which of the following is X in terms of Y, you may want to just model the circumstances by plugging in values for at least one of those variables to determine a possible outcome, as well as some words such as unknown or certain that usually tend to align more with word problems. So for instance, if we were talking about a certain jar of marbles, we could determine the total number of certain marbles. Or if there's just say a vat of unknown size, maybe we can assign a size and model the circumstances for that theoretical rate problem. So let's take a look at a problem solving example. So we've got a sample problem here. You may recognize it from one of our other lessons, and that's because there are more ways to do a problem than necessarily just one specific technical approach. So our modeling problem solving process, you're going to set up the scratch pad listing the choices vertically from A to E, as you will every time. But in this case, you can see highlighted here a couple of the clues we just talked about. We see the phrase in terms of, and we see variables A and B throughout the answer choices throughout the problem itself. So that indicates a possible plugging in values opportunity. So as always, we skip to the end of the problem to identify the sought value and label the choices as such. So we can see if we skip to the end that we're looking for the number of minutes it would take Callum to travel 10 miles at the average of Abby and Barry's rates. So just a number of minutes for C to travel 10 miles, as it were. Then you're going to read from the beginning, taking simplified notes as you go. So we learned that, of course, Abby travels 4 miles in A minutes, so we take that note. And Barry travels 2 miles in B minutes, another note. And then we've got back to the question, which is which of the following represents the number of minutes it would take Callum to travel 10 miles at the average of Abby and Barry's rates in terms of A and B. So Callum equals 10 miles in how many minutes? Then we're going to plug in easy values for the foundation variable or variables dictating the most aspects of the problem. And in this case, it's the A and B minutes. Now, when you plug in easy values, you want to focus on making the arithmetic simple rather than real life. So we're going to pick some numbers for A and B that may not seem realistic. Of course, we don't know how Abby or Barry are traveling here, so it might not be a car, it might not be a train, it might be walking, we don't know. But we're going to just ignore reality, make the math easy. That's the outcome we're looking for. So let's just continue on from step 4 here, and we're going to plug in those easy values. So starting out, we'll just pick A as being equal to 8 and B as being equal to 4, because this is going to produce really easy rates for us to calculate. So we're going to work the problem then using these easy values to model one possible solution. And we know that if Abby travels 4 miles in A minutes, that means half a mile a minute. Similarly, if Barry travels 2 miles in 4 minutes, that's also half a mile a minute, which means that our average doesn't even need to be calculated because it's just half a mile a minute. So then we know that we're trying to solve for how many minutes Callum will take to travel 10 miles. So that's just going to be 10 divided by that half mile per minute, which is 20 minutes. Really simple modeled scenario that we can then use to track our answer choices and which matches this target of 20 when we plug in 8 for A and 4 for B. So then we need to seek that target. So when we divide by 320, we're going to create a fraction in either choice A or choice B, because 10 times AB is going to be 10 times 8, or 80 times 4 is 320, and that's way too big of a denominator. Don't even have to fully calculate this, which is part of the beauty of the process, that you can just eliminate some things as being illogical pretty quickly. Then for 2b plus a, well, that's just going to be 2 times 4, or 8, plus a, which is 8, which is 16, and 16 is not 20, so simple enough. Then for choice D, we've got 10 times ab, which we've already established is 320, and that 320 is going to be divided by 2 times a, which is 16, plus 4, which is 20, and 320 divided by 20 is 16, not the target 20. Now, always check all 5 choices when you're modeling a problem, just to make sure that there wasn't a simple math error somewhere along the line. But sure enough, 320, which we've already established 10ab is, divided by 2 times b, which is 8, plus 8 is 16, and 320 divided by 16 is the 20 minutes we were seeking. And we can confidently select E because it's the only one that matched the model that we had. So just to recap what we just did, step 1 is going to be in setting up the problems, note the clues for the possible modeling opportunity. Those are going to be the variables or unknowns in the problem and or the choices. Also, those key terms of in terms of certain or unknown. Word problems dictated by some sort of unknown, often a total, as well as just simply algebra proving neither apparent nor simple in the moment as you're trying to work through the problem on the GMAT. And don't force yourself to do the technical math. If it's not there, it's better to switch to another tactic as opposed to keep banging away at some algebra that isn't proving basically available to you in the moment. So then, step 2. We need to pick easy values for the foundation variable or variables. So easy values, 2, 3, 5, 10, 100, a half, and relevant factors or multiples. You just want to make the math easy. And so for things like relevant factors or multiples, it may be something like 50 cents for $1, or 120 cents, or 120 minutes for an hour, because those are easily convertible values, because we have to avoid values such as 0, 1, and numbers in the choices or the problem. Because if you've got a number in the choice, it could cancel out exactly to where you create duplicative answers, and that's what we want to avoid. We don't want to have to plug in more than once, and we avoid that scenario if we plug in savvily, and that often involves avoiding numbers in the choices or the problem, as well as 0, 1, or anything that causes weird math. So then step 3 is going to be to work the problem with your easy values to reach one modeled solution. Again, change the numbers if at any point the math gets difficult. There's just no value to being loyal to your numbers if they suddenly become difficult. Then step 4, of course, is to plug your values into the choices seeking a match to the modeled solution you arrive to. You have to test all 5 options to confirm there are no duplicate matches. Test, however, only until the choice does or doesn't match the model. Again, you didn't have to keep going when the denominator was so big in our example, right? You just can stop and say that's a fraction less than 1. I don't need to keep testing. Change a value and retest if multiple choices match your model result, and then stop testing and select when only one choice remains a match. So these are your steps to modeling on the quantitative section when it comes to problem solving. So let's take a look at our second of two tactics we're discussing in this lesson, quantitative backsolving, or plugging in the choices. So this again is going to be an alternative tactic for anything involving complex math or word problems generally. You'll want to note the format of the choices to immediately identify the opportunity, and that basically means that you've got real numbers and they're in ascending or descending numeric order. And once again, just as we did with plugging in easy values, we want to consider this approach as soon as the algebra ceases to be both apparent and simple in the moment. So our backsolving opportunity clues are as follows. First, as I mentioned briefly, numbers and choices in ascending or descending numeric order. So if you've got 2, 5, 10, 100, and 200, then that may be something that you can backsolve. You'll also frequently have a word problem that is seeking a single specific numeric value, and that often is done with the key terms how much, how many, and how old. So if you see those phrases, you might have an indication that backsolving could be a possibility. So we've got a relatively straightforward problem-solving example, and you may be saying to yourself, the technical approach looks okay to me here. But if it doesn't, this is a really easy backsolver if you decide to just look at the best and most efficient path forward in the moment. So that's always the big thing you want to do is stop, consider the best approach, because as soon as you start to think about this, it becomes relatively apparent what the answer must be. So we're going to set up the scratch pad, listing the choices vertically A through E, just as we've got here. Skip to the end, figure out what we're being asked for, and in this case, value of x, it's pretty straightforward, not hiding much here. So there's our x. Now, once again, read from the beginning, taking simplified notes as you go. Again, there's not a lot here, it's just a more technical problem, but 5 to the x minus 5 to the x minus 2 is equal to 120, and what is x? So we can logically estimate to eliminate practically impossible choices immediately, which is really efficient here. So we know that 5 to the x has to be more than 120 because I'm subtracting something from it. That's just logic, right? And no matter what I do, I guess I could technically have it be a negative, but if that were the case, we'd have to have it be really it just doesn't seem logical at all as we even think about it. 5 to the x has to be greater than 120 if I'm subtracting from it. Because if I, again, if I move the thing to the other side, I just know this. I don't need to double check it. So that means I can get rid of A, B, and C immediately. And so that means I can plug in the remaining middle easier choice, which is just 3. And if I plug in 3, I get 5 to the third minus 5 to the 3 minus 2, which is just going to be 125 minus 5, which is 120. And that's our answer. And it's so easy, right? It's so darned easy. So step 1 is going to be to, again, while you're setting up the problem, note the clues for your possible backsolving opportunity. And then those are going to be single numbers in the choices in ascending or descending order. Again, those phrases of how much, how many, how old. A word problem seeking a single specific numeric value. And algebra, once again, proving neither apparent nor simple. Now, step 2 is going to be to logically estimate to eliminate those impossible values. Consider the circumstance of the problem to identify a possible range and assume that real life scenarios are likely to produce integer values. You're not going to have, and again, you're not going to have a negative there. It's just logic. You can focus on this as a logic exam, not necessarily a mathematics one. Then step 3 is going to be to plug in the middle remaining choice to work the conditions of the problem. And you're going to use the columns to deliberately track your required steps. And you're going to set the final column as a condition that must be met. And then our last step, if necessary, because you may not even have to keep going like we did in that problem, we're going to test additional choices using columns for organization, just in case, if there were not a match on the first attempt as there was in the problem there. And as soon as the choice matches all conditions, you select it. You don't have to keep going. If a choice doesn't match, though, you can use it to determine whether you need to go higher or lower through logical estimation. And you can stop testing and select as soon as only one choice remains. So if 3 didn't work there, we knew it was going to be 4 just based on our logical estimation, and we just select 4. We wouldn't have to try again. So that is our back-solving problem-solving process. Let's go ahead and take a look at a couple of example problems together on the whiteboard next. Okay, so let's take a look at this sample problem first. And as always, set up the scratch pad. So we've got A, B, C, D, E, and we skip to the end, figure out what we're being asked for, and we've got how many hours would it take the two of them to knit the same scarf pattern simultaneously? So we're just looking for the combined hours. Equals question mark. And we got 2 2 2/5. We've got 2 1/2. We've got 3, and we've got 5. And remember, if they've got simple numbers, it might be beneficial to write out those answer choices. So we know that Jane is able to knit a certain scarf pattern in 4 hours. Okay, so we know that Jane time is equal to 4. And we know that Mary time is equal to 6. And then we find out that a single scarf can be successfully knit concurrently, and we're being asked for how many hours would it take the two of them to knit the scarf pattern simultaneously. So we actually see here a word certain, and there's an unknown total. So these are indicators that we might have a modeling opportunity. So we just note our modeling clues here. So then we can just decide, like, I don't really know much about scarves, but there's some sort of like total scarf, right? So we just need an easy value. So let's go total scarf is equal to 24 inches. I don't know. I'm not big on scarves. But if that's the case, we know that Jane's rate would be 24 divided by 4 hours would be equal to 6 inches per hour. And we know that Mary's rate would be those 24 inches divided by 6 hours, which would be 4 inches per hour. And then their combined rate is just going to be the sum of those two values. So the combo rate is equal to 10 inches per hour. Which means we can find the combo time by taking the total inches of 24 and dividing it by the combined rate of 10 inches per hour, which, if we simplify that down, is going to end up being 12 over 5, which is equal to 2 2/5 of an hour. Now, is this the only way to solve it? Absolutely not, but it is certainly one way to easily and simply get to choice B. So let's go ahead and take a look at one more example here, and we've got Billy and his baseball cards. So just as we did with the previous problem, we're going to set up our answer choices A, B, C, D, E, and we skip to the end, figure out what we're being asked for. We've got how many cards did he have to start? So cards to start. And we got 50, 75, 100, 200, and 400. So we immediately, before we even do anything here, I'd probably see that my answer choices are in numeric order. So we've got the numbers going up, and we've got that phrase how many. So these indicate possible back-solving clues. Now, then we've got Billy had 800 baseball cards to end last month. So end last month is equal to 800. So then we know that he's been building his card collection by doubling his number of cards each month for the 4 previous months. Okay. And we want to know how many cards he had to start with his collection. So let's just set up some columns. So our start, and then we've got month 1, month 2, month 3, and month 4, because he keeps doubling. And the target is that 800 right here. So let's just try choice C. So if choice C is our answer and we start at 100, then month 1 at the end he's going to have 200. Then at month 2 he's going to have 400. And then at month 3 he's going to be 800, and at the end of month 4 we've got 1600, and that's too high. So we can immediately eliminate not just choice C, but also choices D and E for being too large. So that means we've got to go lower. And so let's just try 75. So if it's 75, after month 1 it's 150, month 2 is 300, month 3 is 600, and month 4 is 1200, we're still too high. And to be perfectly honest, on the exam, we would just select A right now. But to prove it out, just for full completion's sake, if we start with 50, after month 1 we'll have 100 cards, month 2 we'll have 200 cards, month 3 we'll have 400 cards, and after month 4 we've got our target of 800 cards. So you can see in execution, 2 alternative tactics, not the only way, but certainly a very viable way for each of these problems to be completed. So as you continue your quantitative practice problems, think about modeling and backsolving as possible approaches to solve some of these quantitative questions.